All right, here's a wild thought for you. What if I told you that to lower a product's carbon footprint, a factory actually had to burn more fossil fuels? I know, it sounds completely impossible, but it's a real-world paradox in energy accounting. In this explainer, we're going to break down exactly how this counterintuitive math actually works.
I mean, it seems to break a pretty fundamental rule, doesn't it? Burn more fuel and get a lower carbon footprint. But as you're about to see, when you set it up the right way, this isn't some kind of trick. It's very real. So the question is, how is this even possible? Okay, so to really get our heads around this paradox, we first have to look at the original problem. Let's start at a heavy oil extraction facility. This is a place that needs a colossal amount of heat to operate, and that heat is usually generated as steam. And here it is. This is our starting point, our benchmark. In a standard operation, producing just one single barrel of oil pumps out 70.7 kilograms of CO2 emissions. Now keep that number in your head, because that's the number we're trying to beat. So here's the crucial detail. This whole process is pretty inefficient. You burn a ton of natural gas just to make steam, and a huge chunk of that expensive carbon-emitting energy just escapes into the atmosphere as waste heat. It's kind of like leaving a window wide open in the dead of winter while your furnace is on full blast. So what's the solution? Well, engineers looked at all that escaping heat and didn't see waste. They saw an opportunity. They thought, what if we could actually capture that heat and put it to work? And that, right there, is the core idea behind cogeneration. Cogeneration, or CHP, which stands for Combined Heat and Power, is a really elegant concept. Think about it. You're already burning fuel for your main job, right? Which is making steam. Well, cogeneration technology just bolts onto that process, grabs the waste heat, and uses it to do a second job, generating electricity. So you get one fuel source, but two products.
The whole process is actually pretty straightforward. Step 1, that's the same as before, burn gas for steam. But now, step 2 is where things change. You capture the heat that you used to waste. In step 3, that captured heat gets used to generate power. And here's the crucial final step. Any electricity you don't need gets exported to the public grid, which displaces other, maybe less efficient power sources.
Now, this all sounds like a simple, straightforward win for efficiency, right? But this is where our story takes that paradoxical turn we talked about. Because to make this whole system work and generate that valuable electricity, something pretty significant has to change. And there is. You actually have to burn more fuel. To run the turbines that generate all that new electricity, the facility has to burn about 30% more natural gas than it did before. The total amount of fuel being used right there on site goes up a lot. So let's just put them side by side. The base case, that's a standard amount of fuel, and you get one product out of it. The cogen case, you're using more fuel, but you're creating two valuable products. And that distinction, that is the key to this entire thing. Which leads us right to the heart of the puzzle. More fuel means more CO2 is physically coming out of that facility's smokestack. That's just a fact. So how on earth can the official carbon footprint of the oil actually get smaller? It feels like we're breaking the laws of physics here, but we're not. We're just stepping into the wild world of carbon accounting.
You see, the secret isn't in chemistry, it's in the accounting. It all comes down to something called allocation. Basically, it's about deciding how you split the emissions bill when you're creating more than one product. So let's walk through the math, step by step.
Okay, first things first, let's be totally clear. The total physical emissions from the facility absolutely go up. Remember our base case was 70.7 kilograms per barrel? Well, with cogeneration running, the total emissions measured at the site jump up to around 98 kilograms. There's no magic here. More fuel equals more emissions.
But, and this is a huge but, here's the other side of the equation. For every single barrel of oil, the facility is now exporting 86.9 kilowatt hours of electricity to the grid. And that is a second, real, tangible product. In the world of carbon accounting, that product has to carry its own share of the emissions burden.
So this is the rule that changes everything. The emissions have to follow the product. Since that extra 30% of fuel was burned specifically to create electricity, the emissions from that extra fuel are officially assigned to the electricity, not to the oil. And here's how the math actually works out. You start with your total physical emissions, that big number, about 98 kilograms. Then you calculate how many of those emissions belong to the exported power. That's roughly 38 kilograms. So you subtract that 38 from the total,
And the emissions that are left, the ones allocated to the oil, drop all the way down to around 60 kilograms. So here it is, the final results, plain as day. The first bar shows our starting point, 70.7 kilograms. The second bar, that's the net emissions after we apply cogeneration and the proper carbon allocation. The oil's official carbon footprint drops by about 15%, and it's all because we've found a super efficient way to create a second product. It's a really powerful result. But of course, with stuff like this, the details always matter. So let's just quickly touch on the fine print behind these specific numbers. It's really important to note that these numbers are for illustration. The study they came from used outdated emission credits, and it didn't even include the emissions from producing the natural gas in the first place. So you wouldn't use this exact math for official regulatory reporting, but it perfectly explains the principle of allocation. And just one quick clarification. This type of industrial cogeneration is different from, say, a standard high-efficiency power plant. A dedicated power plant uses its waste heat to make even more electricity. Our facility here is making two totally different things, electricity and process steam, and that's what makes this specific kind of allocation possible. Ultimately, it all comes down to this simple idea. By producing two valuable things from a single, highly efficient fuel source, the net emissions for each of those things is reduced. You're just getting so much more value out of every single molecule of fuel you burn. You know, this whole case is a fascinating reminder that how we measure an impact is sometimes just as important as the impact itself. And it really leaves us with a critical question to chew on. If this kind of accounting can completely redefine an emission footprint here, where else might our basic assumptions about environmental impact be, well, incomplete? It's definitely something to think about.